And it's my great honor to participate at this conference. And I also have to thank Professor Pierce for all the discussions, suggestions, and kind help for our team. And also thanks for inviting our team to report this work. And the topic of this report is a non-nested augmented subspace method for eigenvalue problems. Okay, there is the outline of this slide, and following the 8 aspects will be introduced. Okay, as we know, eigenvalue problems are widely used in some fields, such as electricity, Bose-Einstein condensation, and electronic structure calculations. And this feature impaired the flows. Okay, there is some efficient numerical algorithm for solving eigenvalue problems or nonlinear problems. And our team are focused on the finite element method and the multigrid method. So there is some efficient finite element numerical solution method. The two-grid method is proposed by Professor Xu and Professor Zhou in 2001. And my advisor, Professor Xie, proposed a multi-level creation method based on the two-grid method. And this method is extend the two-grid to multi-grid. And the method I mentioned here are based on the nested mesh. And also there is some solver, or you can code a package for solving algebraic eigenvalue problems and algebraic boundary value problems, such as ARPAX, Let's See, and Hyperboom AMG and PASI AMG. And okay, we will introduce our method through a classical model. And here we present a second order Laplacian eigenvalue problems. And the computation rate with curved boundary surface and in 3 dimensions, and with curved boundary edge in 2 dimensions. And here the coefficient A is a SPD matrix. And the element Aij in this matrix are fragmentation constants. Okay, there is a gravitational form for the eigenvalue problems. And we define the norm A and the norm B according to the bilinear form. And before we calculating, we should divide the computational rate omega to get the mesh T capital H. And the T capital H is the closed mesh in this situation. And we also use the linear finite element method to discrete U and get finite element space V capital H. And the V capital H is equal to the VH1. And how we obtain the fine mesh TH? We use the adaptive refinement the closed mesh T capital H according to the function of the curved boundary surface in advance to obtain the fine mesh TH. Okay, so we know the nesting relationship between V capital H and VH is not satisfied. And why we do need to use non-nested mesh instead of nested mesh? It's because of the curved boundary surface. If we only use the nested uniform refinement, the approximate accuracy of the curved surface will not be improved. And we also find even if the augmented subspace we built this V capital H and at span the U tilde H is not a subset of the VH, but it's still a subset of the source space. So the optimal convergence accuracy can still be obtained. And also we can combine with some mono mesh or adaptive technique on this method to furthermore improve the discrete efficiency. And okay, there is an Nonnested augmented subspace method. And assume that we have the input approximate eigenpair lambda u has been obtained, and the augmented subspace algorithm is declared as flow. And we can call this algorithm 1 is a one question step. And in this one question step, it contains 2 steps. And in the first step, we should solve the linear boundary value problems on finite mesh VH and the TH also. And because we have no nesting relationship between the different grids, so we have to use the AMG method to solve these boundary value problems. And in the second step, we define an augmented subspace with capital HH. And we solve the original eigenvalue problems on this low dimension subspace. And then we should obtain the new output eigenpair. Okay, there's our estimate of the algorithm 1 has been given, but I have not much time, so I will skip it. If you're interested in, this work has been linked to the archive. You can research directly. And it was mentioned that if the cross mesh is small enough, and the computational work included in algorithm 1 is nearly a linear complexity. Okay, and how to implement this algorithm in FreeFEM? Because we have no nested relationship between the V capital H and the VH. So we have to use the iteration operator from FreeFEM function, for example, interpolate or transformat, to build the connect from the VH to VH. And if you remember, in the algorithm 1, we should solve the eigenvalue problems on this special space with capital HH. So we have to form this algebraic formula to solve the eigenvalue problems. And here, in order to ensure the approximate accuracy of the curved boundary surface, so when forming the A capital H, we need to integrate on the finite mesh TH, it's not the T capital H. And for now, we just only assemble A capital H by some algebraic form. For example, the A capital H is equal to P transpose times AH times P. And the vector AH is equal to P transpose times AH times U tilde H. And the number alpha is equal to the U tilde H transpose times AH and times U tilde H. But if we need to solve the nonlinear eigenvalue problems, we need to assemble the fan matrix AH to obtain the A capital H in each nonlinear iteration. And the cost for assemble matrix is very large. So how to efficiently assemble it is still a question. Okay, if we can generate several of non-nested meshes, we can extend to multi-grid method, and we can build a corresponding finite element space with HK. And K is the number of the layers. And the multi-level regression algorithm is described as the algorithm 2. And the first step in algorithm 2, we should obtain an approximate eigenpair by solving the eigenvalue problems on the initial cross grid VH1. And then we perform the capital L times one question steps on each finite linear inter. And finally, we can obtain the approximate eigenpair on the finite layers. Okay, here we get some error estimates of the multi-level regression algorithm. After running algorithm 2, we can get the optimal error estimate for the eigenpair. And the total work of algorithm 2 is shown here. Okay, now we do some numerical test. This is two-dimensional Laplacian eigenvalue problems, and we have a fragmentation confidence A, and the computation error has to curved boundary surface in this case, and the computation error we generated by the mesh function border and adapt mesh that comes from FreeFEM. And there's the picture of the two cross mesh T capital H for example 1. And the left has 515 elements, and the right one have linear 1,500 elements. Okay, and here's the error estimate for the first floor and the 10th eigenpair error estimate by algorithm 2. And it can be seen from the picture that if the cross mesh is get thinner and the convergence of the eigenpair is faster, you can see the top two figure have 12 iteration times, but the bottom of 2 is only need the 4 iteration times. Okay, here's the CPU time for algorithm 2 with 33 process. And both of these are linear complexities. And so for now, we propose an augmented subspace algorithm for solving eigenvalue problems on regions with curved boundary surface, even there's no nesting relationship. And furthermore, for some nonlinear eigenvalue problems, we can use this algorithm combined with some moving mesh or adaptive technique to further improve the decrease efficiency. And now we focus on the GP equation. And the GP equation describes the ground state solution of Bose-Einstein condensation. And the equation we list here is the simplified steady state GPE posed by Professor Bao and Professor Tang in 2003. And you can see this is nonlinear eigenvalue problems, and the VEST is the potential function. And you can see the nonlinear term in this equation is polynomial. And the C is the nonlinear coefficients, and the E is the energy. And the variational form is shown here. This is the multi-level correction method with moving mesh for GPE. And the GPE solver in this case is based on the Pika iterations. And the difference between this algorithm and the algorithm 2 is that we start from the cost layers calculated the energy difference delta E between the grids according to the solved eigenfunctions, and use this eigenfunction U to measure the mesh movement. And then we can similar as the Laplacian eigenvalue problems is to do the one question step. Okay, and how to implement with FreeFEM in this case, and we use R adaptive method to design, and we use the measurement and MMG3D in FreeFEM, and we use the eigenfunction U to measure the mesh movement. And similar as the Laplacian eigenvalue problems, we also have to solve the eigenvalue problems on our augmented subspace. So we also use the algebraic symbol form of algorithm 1 to form this algebraic form. And this is a discussion, can it be implemented efficiently? And the answer is yes, if FreeFEM can define the tensor T capital H. And because the matrix A capital H can divide it by some terms, and the AH1 and the AH23 will not change during the nonlinear iteration process. And the AH22 can equal to multiplications of the tensor TH and the vector U capital H. So if you want to learn details, you can research this paper. It's proposed by my supervisor, Professor Xie, in 2019. Okay, and now we do some tests. We solve the cubic GPE with 72 process. And the nonlinear coefficient C is equal to 1, 100, 200, and 400. And from the figure A and figure B shows the CPU time using AFEM and our adaptive multi-level correction method. It can be seen that both of these two methods have asymptotic optimal linear complexity. But our adaptive MLC method has a great advantages in computational efficiency. Not only its calculation time is greatly reduced, and more important that the CPU times reduced. This depend on the strength of nonlinearity. Is the C. Okay, and the follow three tables list the CPU time compare between the multi-level correction method and AFEM. And we can see if the size of the problem is large enough, and our method will have a great advantages to solve this. And it's necessary to mention that the CPU time showing here does not include MMG part because the MMG 3D is a serial mesh generatory. So the time of this part is very large. And okay, here we show the picture of the ground state wave functions. For example, the adaptive mesh for D2G. And now we focus on the constraint equations. And the constraint equation is one of the most important model equations in the calculation of electronic structure, and it's also a tactical nonlinear eigenvalue problems. And now we shown these equations and his variational form for this. Okay, we do test for lead hydrogen molecules in FreeFEM software with 72 processes. And here the CPU time is similar as the GPE functions. If the set of problem is large enough, our method have great advantages. And there's a picture of electrodensity and ground state energy is given below. Okay. And here we will talk about the computational bottleneck in the test. And there is 3 points. And the first point is so far the cost grade T capital H in above mentioned numerical tests are global. So we can use the interlate function in FreeFEM, and this function has a good parallel scalability. But if we use the cost mat, is also parallel. The parallel scalability of transfer mat is still challenging. And the second point is the CPU time of several moving mesh operations. For example, the serial MMG are very large. But luckily, Professor Pierre will introduce the power MMG in FreeFEM, so we hope that this operation will reduce the overall calculation time. And the last thing is because we need to ensure the approximate accuracy of the fan grid, so we have to assemble the matrix on the final grid TH. But we also use the basic function in the cosmatch V capital H. And for now, we just only can, from the algebraic form, to do this A capital H. For example, the A capital H is equal to the P transport times AH times P. So if it's possible to directly assemble this form. If it's possible, then the cost of assembling matrix A capital H will reduce. Okay, and there's the small summary. And we put an augmented subspace method based on non-nested and adaptive mesh to solving nonlinear problems. And this method essentially solves the linear boundary method, linear boundary value method problem on the phi linear, and solve the nonlinear problems on a special augmented subspace. So the work of this calculation is greatly reduced. And if the tensor data structure and the product operation of the tensor and the vector can be realized in FreeFEM, then the computation work can be the same as the linear Laplacian equation for the nonlinear term with polynomial form. And in our future work, we will apply this method to solve PB equations and TMP equations in biology fields. And thanks again, Professor Pierce, for our help and kind discussions. And thanks all for your attention.
So thanks for these excellent talks. There are some questions before the small break, coffee break.
I have a couple of questions.
Yeah.
So you said that the MMG timings were large. Can you just give an idea of the timings compared to the method, just to get a quick idea of the comparison between the algorithm itself and the mesh adaptation, which is done in sequential for now?
Okay, but you not mention here. Hold on a second.
Yeah, just an approximation. Is it like 100, 1,000, 10,000 seconds?
And the MMG part, at the time of MMG part, is almost 70% for this CPU time. So we not list for here.
Okay. And so you don't care about the boundary of your, I mean, from the picture you showed, it looks like most of the mesh evolution takes place in the center of the domain. So I guess you don't really care about adapting the surface of the bounding box, right?
Oh, yeah.
Okay. So this is actually a scenario in which we could try ParMMG, because right now it does not handle surface adaptation, but maybe we could try it. Okay. Thank you.
Thank you.
Okay, another question. So I think no more. So I say,
thank you.
Bravo.